Okay, so now we're on to section 2.8, and we're talking about the derivative as a function. Now, the last example I presented in the previous video suggested that, hey, I can compute a derivative at every single point at once. If I have a formula for something at every single value at once, that's a function. So really, we can look at the derivative as a function, and then we can use all of the tools of studying functions to study the derivative. Great. So here's the definition. The derivative of f of x is the function defined by f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. It's a subtle difference from what we were talking about in the last video. In the last video, I was imagining the derivative as a value, a number. C was a specific number. Plugging it into the formula gave me a specific number. Now I'm imagining that this is a function, and I'm interested in what happens to it as x changes. Now, one way that we like to study functions is to look at the graphs. So we can actually pretty quickly sketch the graph of a derivative just by looking at the graph of a function. We're just going to use three basic facts. When f of x is increasing, then it has a positively sloped tangent line. Since the derivative is the slope of the tangent line, that means that if f is increasing, the derivative is positive. If f of x is decreasing, then it's got a negatively sloped tangent line. So that means that the derivative will be negative there. Finally, when the function is flat, by which I mean it has a horizontal tangent, well, the slope of a horizontal line is 0, so the derivative will be 0. So in this graph over here, I've drawn some function. I should have labeled it y equal to f of x, so let me do that. And down here, I've drawn the graph of its derivative. Great. And I've drawn increasing in positive green, decreasing in negative red, and flat and 0 as blue. So with this function here, probably the best thing to do first is to find the places where it flattens out. Right up here, down here, up here, down here. It tends to happen at maximums and minimums. Not always, but at least in the picture I've drawn here, that's so. So to start sketching the derivative, I will take the places where the derivative is 0, and I will plot 0 on the graph of the derivative. Then I identify the intervals on which the graph is increasing or decreasing. It will always be increasing or decreasing between any two of these places where we have a horizontal tangent, at least in my picture. So from here to here, it's increasing. From here to here, it's decreasing. From here to here, increasing. From here to here, decreasing. From here to here, increasing. So wherever it's increasing, I should draw the function so that it's positive. The derivative so that it's positive. Where it's decreasing, on these two intervals, I should draw the derivative that it's negative. And I guess I'm just inclined to try to draw the derivative so it's continuous. Is that always going to happen? Well, that's not necessarily always going to happen, but I've drawn it that way here. Okay. So now let's do an algebraic example. Let's let f of x be x cubed minus x, and let's find f prime of x. We're doing this from the definition. If you've seen the power rule before, you know a faster way of doing that. Slow down. We're going to do it this way right now. Okay, so by definition, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. So I plug x plus h into x cubed minus x to get this, and then I subtract f of x. I multiply out, and I'm left with x cubed plus 3x squared h plus 3x h squared plus h cubed. Pause the video and verify that that is correct. Okay, minus x minus h, and that comes from the first piece. And then I distribute the negative for the second piece. I get minus x cubed plus x. Now I cancel like terms, or I combine like terms. This x cubed and this minus x cubed cancel. Negative x and x cancel, leaving me with 3x squared h plus 3x h squared plus h cubed minus h all divided by h. Well, everybody up top has a factor of h. So if I factor that out, I get 3x squared plus 3xh plus h squared minus 1 all times h divided by h. Those cancel. leaving me with 3x squared plus 3xh plus h squared minus 1. Now I can evaluate the limit. Plug in h equal to 0. This guy and this guy go away, and I'm left with 3x squared minus 1. That is my formula for the derivative. It's instructive for us to compare the graphs of the function x cubed minus x and its derivative 3x squared minus 1. So up here I have x cubed minus x. It has roots at -1, 0, and 1, and it more or less looks like this. Here's the graph of 3x squared minus 1. It's a parabola opening upward with a vertex at 0, -1. Note where x cubed minus x reaches a maximum or a minimum where it flattens out. That corresponds to the roots of the derivative, where the derivative is equal to 0. That's what we expect. Furthermore, the graph of x cubed minus x is increasing to the left of the first root. That's similar to the graph down here being positive, so increasing function corresponds to positive derivative. And it's increasing to the right of the second root, and the derivative is positive to the right of the second root. And between the two, these two values, x cubed minus x is decreasing, corresponding to the fact that the graph down here is negative between the two roots. Let's do another example. Let's find the derivative of g of x, which is the square root of x. By definition, g prime is g of x plus h minus g of x over h as h goes to 0. Again, the problem with all of these derivative limits is if I just plug in 0, I get g of x minus g of x over 0. We get 0 over 0. So we need to be able to factor out an h on top and cancel it with the h on the bottom. So I replace g with its definition, which is the square root. So on top I've got the square root of x plus h minus the square root of x. When we've seen that before, we've realized what we have to do is multiply the top and bottom by the conjugate of the top, which is the square root of x plus h plus the square root of x. So doing that, I obtain this expression. Don't multiply out down here because we're eventually going to want to cancel h. If you multiply out, you're going to have to factor h out again in order to cancel it. Don't multiply out. Leave it like this. Stop. Leave it. Please. Okay. Fine. So now this is a minus b times a plus b. So I get the difference of their squares. The square of the square root of x plus h is x plus h. The square of the square root of x is x. X plus h minus x gives me h. And there's the h that I wanted to cancel out. This h downstairs that I didn't multiply through, and this h upstairs cancel out, leaving me with a limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now I can plug in 0. Why? Because this is defined so long as x is positive when I plug this in. So I get 1 over the square root of x plus the square root of x, which is 1 over 2 times the square root of x. Okay, so here's the question for this video, question number 2. A, let capital F of x be 1 over x. Find capital F prime of x. Hint, when you manipulate the numerator, you're going to have to find a common denominator for the fractions up there. B, once you've found formulas for these guys, well, for this guy, graph both of the functions. Use an online graphing utility if you want to. That's fine. And to compare the graphs of capital F and capital F prime, and in particular, see how increasing over here corresponds to positive over here, decreasing over here corresponds to negative over here, and if it happens, horizontal over here corresponds to 0 over here.